Hi everyone, and welcome to the final lecture for the course Hardware Systems Applications. Today we are going to be covering finite state machines. Just really quickly, an overview of what we're going to be doing today. We are going to look at exactly what a finite state machine is and the different ways that we can represent a finite state machine. Particularly, we are going to focus on state transition diagrams. And we are going to look at two different types of finite state machines. These are the Moore machine and the Mealy machine. Then we are going to look at some examples with particular attention being paid to sequence detectors. And finally, we are going to look at how to write the VHDL code for a finite state machine, as this is very important for our exams. So we know that there are two types of logic with which we are familiar. These are combinational logic and sequential logic. Of course, we know that combinational logic is logic which firstly does not require a clock signal for operation, and secondly, it is logic which typically does not exhibit memory, whereas sequential logic is defined by those two things. It first of all requires a clock signal, and secondly, typically, it exhibits memory. Now, a finite state machine, or an FSM for short, is a sequential machine with random next state logic, and that is the baseline definition for a finite state machine. Finite state machines are used to implement functions that are realized by carrying out a sequence of steps and are commonly used as controllers in large systems. So one of the most important things to understand about finite state machines is that they represent a sequence of steps or a series of steps and how we can transition from one state to the other. So a formal definition is a finite state machine is a computing machine with a fixed set of possible states, a set of inputs that change the state, and a set of possible outputs. The phrase fixed set of possible states is another way to say finite states. Of course, we know that finite is a keyword here since we implement a finite state machine in hardware or software. Because it's being implemented in hardware, we cannot have unlimited resources, okay? All right, we have a limited amount of memory to play with. So from this definition, what this implies is that if some design were to be based on a finite state machine, that means that this system or design can be in one of any number of states. We always know the number of states that exist. And based on the input to the system, we transition or we change from one state to the other. And in each state that we are in, there's some set of possible outputs for that state. So FSMs consist of a set of states, some inputs, some outputs, and a set of rules governing the transition from one state to another. It's important to note that the new state or the next state that we are going to be transitioning to is a combination of the current state that I am in as well as the input value to the system when I am in that current state. So a finite state machine is specified using 5 entities. These are symbolic states, inputs, outputs, some next state function, that's the actual rules that govern the transition, and an output function, which tells us what is the output when I am in a particular state. In digital design, it is very common to begin by defining how the system works with an FSM model. It allows the designer to think about the design from a high-level perspective without having to think too much of the underlying implementation. And once the FSM is fully designed, well, it's easy to write out VHDL code from there. And what that means is that when the VHDL code is synthesized into hardware, we do not need to think about how the hardware is implemented. Instead, all we need to do is write the code for this FSM, define these rules that allow us to transition from one state to the next, and when it's synthesized into hardware, it is going to put together the underlying components for that FSM to be realized. Just reading the last sentence and the last point here, modeling an FSM requires the use of a state diagram. We said that a state diagram is one way to potentially represent a finite state machine. So let's take a look at what a state transition diagram or an FSM diagram looks like. Now, FSM diagrams or state transition diagrams are made up of a number of these circles or bubbles that we are seeing on the screen right now. Each of these circles represents a particular state. All right, so the node or the bubble represents some unique state. So if a system that we are designing can exist in 4 possible states, then this will be represented in a state transition diagram with 4 different bubbles or nodes here. All right. Now, out of each of these states or flowing into one of these states are these arcs or arrows, which represent the transitions from one state to another. So we can have arrows flowing out of that state bubble, or we can have arrows flowing into the state bubble. All right, so the annotations for the arcs or the arrows show the rules which allow us to change from one state to another. All right, now there are different ways to represent the outputs, and these are dependent on the type of finite state machines that we are designing. All right, but before we get to that, it's important to note that there may be some logical expression along that arrow or that arc which allows us to transition from one state to the other. So I'm just going to bring up this laser pointer here. So we are focusing on this field here on the left-hand side of this slash. We'll ignore what's on the right-hand side for now. All right, so reading this point here, the arc or arrow shows the rules for changing from one state to the next, and it is labeled with the condition that causes that transition. Those logical expressions are actually the inputs to this particular state which causes that change. Now, for more state machines, the outputs of a particular state are shown inside the bubble like this. For Mealy machines, however, the outputs are shown on the right-hand side of this forward slash on the transition or the arc. And we will see this in a little while to get a better appreciation of this distinction. All right? So let's take a look at a simple state diagram here. In this state diagram, as we can see, there are 4 states: S1, S2, S3, and S4. All right? S1 is the initial state that the system is in. We know that this is the initial state because it is denoted by this random arrow that's coming from nowhere. All right, so whenever we see, typically there's a little dot on the other side of this arrow. Whenever we see an arrow with a dot flowing into some state, we know that that is the initial state in our design. S4 is the final state, which is denoted by these 2 circles here. Now, this is not a very commonly used representation, the 2 circles. However, in our state transition diagram, we must definitely have this reset or initial arrow here. All right? Note that from this note here, it says in digital design, we will not use this final state notation. All right, now to interpret the diagram, we're going to look at the inputs to each state and how the logic expression made up of these inputs causes some transition from state to state. So let's just say we have some design diagram. All right, I'm going to try to draw it here now. Let's just say we have some schematic that looks like this. All right, and into my design here, I have 4 inputs: A, B, C, and D. All right. So these are the inputs to the system. The system, however, itself can exist in one of 4 states. These are S1, S2, S3, and S4. Now, when I'm in state S1, all right, and there's some input on input A into the system, I'm going to transition from state S1 to S2. Likewise, when I'm in S2 and B is input into the system, or there's some input on input B, I'm going to transition back from state S2 to state S1. When I am in S2 and I receive input C, I'm going to transition to state S4. S4 can transition to S3 if input D is applied. And if I'm in state S3 and I receive input B, I'm going to go back to state S4. If I receive input A, I'm going to go back to S1. All right. This little portion of the diagram was cut out on the previous slide, but in this case here, this arrow or this arc, which shows us a transition from the state back to itself, what this means is that if I am in S2 and I receive input A, I do not change state. The state transitions back to itself. All right, so on the side here, we just have an explanation of exactly what this state diagram is doing. So when in S1, input A causes a transition to S2. In S2, input B, which forms the logic expression for the transition, results in a transition back to S1. Also, in S2, input A results in S2 transitioning to itself. S2 is therefore in a waiting state when the input is A. Take note that these transitions here, these logic expressions, imply the inputs to the overall system when I am in a particular state. All right? So when I'm in state S2, an input C causes the transition to S4. In S4, an input D results in a transition to S3. Despite being the final state, despite the fact that S4 is the final state, there can still be some input into that state. All right. In S3, input A and B result in transitions to S1 and S4 respectively. All right. We're going to see many more examples of this to kind of clarify how those inputs work in relation to the states. All right. Now there are two types of finite state machines which we will be looking at. These are the Moore machine and Mealy machines. All right. Now, in Moore machines, the transitions or the arrows indicate the inputs, and the outputs of a particular state are indicated inside of the state bubble itself. In Mealy finite state machines, on the other hand, the inputs and the outputs are indicated on the transition arcs or on those arrows, and they are separated by that forward slash. All right, everything before the forward slash are inputs to the system when it's in a particular state, and everything after the forward slash results in it implies the outputs that are resulting due to that input. So let's take a look at the Moore finite state machine. The FSM has 4 states here: A, B, C, and D. All right. Just sorry about that. So when I'm in this in this finite state machine here, I have 4 states: states A, B, C, and D. The system has one input signal P. All right. Note that when P can take on a value of either 1 or 0. P is just some binary signal. All right. So the value of P determines what state the system moves on to next. Remember we said on this slide earlier here that the new state that I'm transitioning to is determined based on the current state that I'm in, as well as the input when I'm in that current state. All right, so back to this finite state machine here. Based on this diagram, we can tell that the initial state is state A. I know this because this arrow that's coming from nowhere denotes state A as my initial state. What that implies is that if I design a system, on startup of that system, I'm going to be in state A. All right? Now, when I'm in state A and input P is equal to 1, what that implies is that I will transition to state B. Before we even look at this transition, note that when I'm in state A, my output R is equal to 0. So let's see if we can actually draw that to see how that will look here. This system, all the system has is an input P and an output R. All right, this output R is only going to go high when I am in state D, as you can see here. All right, okay, so in state A, my output is 0. When P is equal to 1, I'm going to transition to state B. In state B, my output is still 0. When I'm in state B, if P is equal to 1, that is going to trigger a transition to state C. Of course, in state C, my output R is equal to 0 again. When I'm in state C and my input P is equal to 1, I'm going to transition to state D. And it's only when I'm in state D that my output R is high. When I'm in state D, if P is equal to 0, I'm going to go back to my initial state. Or when I'm in state D and P is equal to 1, I'm going to transition to state B. What about when I'm in A, B, or C and P is equal to 0? Well, even though these values are not stated in this state diagram, what's actually going to happen here is when I'm in state A and P is equal to 0, nothing happens. So I'm just going to stay in that state. In other words, this state transitions back to itself. Likewise, when I'm in state B, if P is equal to 0, I'm just going to stay in that state. So we see here that only when P is equal to 1 in states A, B, C, and as well as D, that is when some transition is triggered. Okay, so quickly reading from the slides, a finite state machine has 4 states, A, B, C, and D. The system has one input signal, P, which could either be 0 or 1, and P, the value of P, determines which state the system moves on to next. The system changes state from A to B to C to D as long as P is high. If P is low and the system is in state A, B, or C, this state is not changed. If the system is in state D, it changes to state B if P is high and to state A if P is low. The system also has an output called R, which is 1 if it's in state D and 0 otherwise. The information underneath the line in the circle represents the output value when I'm in a particular state. That's these values here below the little line in the bubble here. Now, these Moore machines are typically the easier one for us to deal with. All right. If in an exam we are asked to draw a state machine or a state diagram or some FSM for a particular system, this is typically the paradigm that we will use, the Moore machine. That is not to say that we will be limited to Moore machines. If we have a better understanding of a Mealy machine, that is also applicable. All right, and we look at both of them when we're looking at the past papers to see how these are drawn in an exam. All right, so we're looking at another example of a Moore finite state machine here. The premise behind this state machine is I have, say, a lamp, a bedside table lamp, and there's a string to pull on that lamp. All right, And when I pull the string, if the lamp is off, the light is going to get dim. When I pull the string again, the light is going to get brighter. When I pull the string again, the light is going to be on its brightest state. And when I pull the string in the brightest state, I'm going to turn the lamp back off. All right, so this is just a simple and a pretty common example of a more finite state machine. In this 3-intensity light, I only have one input, and that's just some click. It's denoted as a click here, but that just implies me probably touching the lamp or pulling on some little string or something like that. The lamp is off, and I touch the lamp or I pull the string, the light is going to turn on, it's going to be dim. If I do that again, the light is going to go on to medium. If I do that again, the light is going to be in its brightest state. And when it's in the brightest state, if I pull that string or I touch the lamp again, the lamp is going to turn off. Now, despite the fact that this is a more FSM, you may be saying, well, hey, there isn't an output in this diagram. There's only these state names here. But because of the nature of this state diagram, this is pretty self-explanatory. In other words, the state name itself actually implies what is the output of the lamp in that particular state. All right, so this is just another example of a simple more FSM. Let's take a look now at Mealy machines. Now, in a Mealy finite state machine, we do not show the status of the output inside the state bubble. It is shown in combination with the input conditions which cause the transitions. All right, I'm just going to repeat that again. In a Mealy machine, the output itself, we don't show that output inside the bubble. So kind of like how we had R equals 0 here, we won't have this in a Mealy machine. Instead, we would have represented this output on the transition arc itself. All right. In more machines, that's the one we just looked at, the output is a function of the current state only. In Mealy machines, the output is a function of the current state and the current inputs. Consider the Mealy equivalent of the 3-intensity light. In this case, we represent the 4 states with different names here: 0, 0, 0, 1, 1, 0, and 1, 1. In state 0, 0, previously we were denoting the dim output, we no longer have states like off, on, off, dim, medium, bright, etc. The outputs of the lamp are denoted on these transitions here. So when I'm in state 0, 0, we are assuming that the lamp is off. This is my initial state. When I touch that lamp or I pull that string on that lamp to turn it on once, the input to that is that click, and the output as a result of that input is the light emitting some sort of dim brightness. And then I transition to state 0, 1. Notice in this case, we do not say that in state 0, 0 the light is off, or in state 0, 1 my output is dim. Instead, I just have the names of these states, and the outputs are denoted on the arc. Remember, the output is just the intensity of the light. All right. Again, when I'm in state 0, 1, we are assuming at this point, to get to this state, the output was this dim light. Then, when my input is me pulling that string on the lamp again, or touching the lamp, or whatever it is, the output of the bulb is now some medium brightness, and I transition to the next state. Again, my input to that state is me triggering the lamp, and that is where I'm going to output the brightest intensity of the light, which takes me to my final state. And then, when I apply that input again, previously the output off was denoted in this state bubble itself. Now, that output is denoted on the right-hand side of this forward slash here. All right, so the output of the system, which is turning the lamp off, is denoted along the transition, and we go back to this initial 0, 0 state here. All right. Now, in my opinion, Mealy machines are a little more involved, and they're a little harder to learn. It's easy for us to denote the output of a system when we are in a particular state, which is why I typically advise for us to stick to more machines, because they're a little more intuitive and a little easier to reproduce in an exam. All right, so let's look at something called a sequence detector, and we're going to look at example of this sequence detector with a more FSM and a milli FSM. So here we have some system, all right, which what this system is going to do is it's accepting some bit string, right? And when the bit string that I'm accepting exhibits a sequence of inputs 0, 1, 1, I'm going to output a 1 on my output. Otherwise, I'm going to output a 0. So again, just to clarify what this system is going to look like, right, I'm going to try to draw this system here. All right, just excuse the scrappy drawing. I'm kind of using my mouse to draw. I don't really have a stylus or a tablet to draw. All right, so we have one input, one output. This input here is some sequence of bits flowing in one at a time. All right, and whenever the input here is 0, 1, 1, I'm going to output a 1 here. Otherwise, I will be outputting a 0. All right, that's just a little overview of what the system is going to look like. This is what we call a sequence detector. And for those of you who would have done digital electronics, you'd be quite familiar with this. So let's take a look at this Moore diagram here to kind of understand what's going on here. So we have 4 states here in this diagram: state 0, 0, 0, 1, 1, 0, and 1, 1. Alternatively, I could have labeled these states A, B, C, and D. Really doesn't matter. What is important, however, is that we know which state is going to give us a high output. And we know that in order to produce that high output, I must have a series or a sequence of inputs of 0, 1, 1. Right? I know that this state 0, 0 on the left here is my initial state. Of course, that is denoted by this dot and this arrow here. When I'm in state 0, 0, and I receive this first 0, 0, that's allowing me to transition to the next state. When I'm in state 0, 1, I'm not outputting a high because thus far I've only received a 0. I have not yet received 0, 1, 1. All right? In this state here, when I receive a 1, that's the second one here, I'm going to transition to the next state here. Again, in this state, I'm going to output 0. In this third state, when I receive this input 1, I'm going to transition to my last state here. To get to this final state here, I would have had to receive inputs 0, 1, 1 in that order. And we see that when I received those inputs 0, 1, 1 in that order, it allowed me to transition to this final state. In order to get to this final state, again, I would have had to receive 0, 1, 1. And of course, because of that, in this final state here, I'm allowed to output a 1 because the problem said to output a 1 when my inputs have this sequence 0, 1, 1. Otherwise, output a 0, which is why we're outputting zeros in all these places here. So what does that mean? What that means is my sequence of inputs, right? If I receive a 0, I'm transitioning from this first state to the second state. If I receive a 0 again, do I want to move forward to the next state? No. I'm just going to wait in this state here until I get a 1. And it's only when I receive that 1, that's when I'm going to transition to the next state. When I'm in this next state, right, so let's just say I'm receiving a series of zeros here. I'm going to move from this first state to this second state, and I'm going to be continuously staying in this second state until I receive a 1. Let's just say I receive my first 1 here. That allows me to transition to this third state here. But I have not yet received 0, 1, 1. I only received 0 and 1, so I can't output a high yet. What happens if I receive a next 0 again? Well, I can't transition forward to the next state. But at the same time, I can't also stay in this state, because to get in this state, I would have had to receive 0 and 1. So what that means is if the sequence of inputs is now 0, 1, 0, that 0 there is going to take me back to this state to wait on that 1. Why? Because after this 0, 1 here, if I get another 0 again, that takes me back to the beginning of this sequence where I have to wait for another 1 in order to transition, and then possibly another 1 again. All right, so let's just say I received this second 1 again. That means that I am in state 1, 0. In state 1, 0, I accept another 1 again. All right, what that implies is that I have received the desired sequence of inputs, which is why I transition into this state here. And once in this state, I'm going to output this 1. Now, when I'm in this state, all right, if I receive a 0, the sequence of 0, 1, 1 has been broken. Likewise, if I'm in this final state here after receiving 0, 1, 1, and I receive a 1, again, the desired sequence is broken because the sequence is broken because I do not have the sequence 0, 1, 1 here. Note that this is 1, 1, 1. Likewise, if this was 0, 1, 1, 0, the sequence has been broken. All right? So when I'm in this state and I receive a 0, what that means, right? So let me just clear up the top here. All right, so we're going to look at this first case here, right? I've received 0, 1, 1. So I know for sure I'm in this final state and I'm outputting the value 1. If I receive a 0 again, well, that could potentially be the start of another 0, 1, 1 sequence, which means that when I'm in this state and I receive a 0 input, that is going to take me back to state 0, 1 here. It's important for us to understand why we're going back to state 0, 1 here. Because from my initial state, the inputs which allow me to transition to this state is always going to be a 0. Notice there's a 0 here and there's a 0 here. After this sequence 0, 1, 1 here, if I receive a 0 again, I'm just going to reiterate this again, it could potentially be the start of another 0, 1, 1. We don't know if the next thing is going to be 1, 1. However, assuming that it could potentially be the start of another 0, 1, 1, we have to come back to this state here, which, if I receive that 1, 1, would allow me to come back into state D here, or my final state. If I'm just going to erase this diagram a little bit to make it a little neater. All right, if I am in state D or state 1, 1, that's my final state here, after I've received 0, 1, 1, and I receive a 1, well, that can't be the start of another 0, 1, 1 sequence because, well, there's not a 0 here. And what that means now is that if I'm in state D here and I receive a 1, I'm going to go back to the initial state, which allows me to wait for that 0, 1, 1 again. All right? It takes a lot of understanding and a lot of time to understand sequence detectors. All right? And hopefully once this entire COVID-19 situation is over, we could probably get back to actually explaining this in class. All right. Let's take a look at how we can write or how we can draw a state transition diagram for the same sequence detector, but using the Mealy methodology. Again, we would like to output a 1 on the sequence of inputs 0, 1, 1. All right. Now, if I'm in my initial state here, and of course, this initial state is denoted by this dot with the arrow coming from nowhere here. If I'm in this state, remember, in the case of the Mealy machine, my outputs are specified on my arcs. My outputs are no longer inside of the bubbles. All right. So if I'm in state 0, 0, and I receive that input of 0, my output is going to be 0 because I have not yet received the sequence 0, 1, 1. If I receive the second 1 in the sequence here, I'm going to go to this third state here. Again, my output is 0. And in this final state, if I receive an input of 1, my output is going to be high. However, after I've received this sequence 0, 1, 1, and I receive another 1, I know I would like to go back to this initial state here. Likewise, if I receive the sequence 0, 1, 0, I'm going to go back to this second state here. All right, so let's just try to draw this out a little bit here. Let's just say we have this potential sequence here. And we're going to try to use this sequence to predict the output here. All right. When I'm in my initial state and I receive an input of 0, that could potentially be the start of a sequence 0, 1, 1. So I'm going to have to transition to the next state here. However, I have not yet received the full sequence 0, 1, 1, so my output is 0. When I receive a 0 here in my second state, I can't transition forward to the next state, but at the same time, that could potentially be the start of a 0, 1, 1 sequence. So I have to wait now in this second state, which allowed me to start this potential sequence and await a further 1. All right. Now the next bit in line here, or the next input in line, is a 1. This 0, 1 here could potentially belong to a 0, 1, 1 sequence, which means that now I'm going to transition to my third state. However, during this transition, I have not yet received the sequence 0, 1, 1, so again, my output is 0. Now, when I'm in state 1, 0 here, and I receive this 0 here, that actually breaks the sequence 0, 1, 1. What that means is I'm going to go back to the second state where I wait again for another potential 1, because again, this 0 could imply the start of a 0, 1, 1 sequence, which is why I transition back to this state here. All right, now when I'm in state 0, 1, and that's for this bit here, when I'm in state 0, 1 and I receive this 1 here, again, that's a potential 0, 1, 1 sequence. So I'm going to transition to state 1, 0. And then when I receive this third 1 here, and I'm in state 1, 0, notice that the input here of 1 it gives me the output of 1 and it allows me to transition back to state 0, 0. Now back in state 0, 0, if I receive this input of 1, of course, keep in mind that that breaks the sequence. And in breaking the sequence, I'm going to stay in this initial state here. That's this transition here. All right? Now, the biggest takeaway between mealy and more machines is if I am required to write or draw a finite state machine diagram for n bits in a more machine, I'm going to use n plus 1 states. Note that my sequence is 3 bits here, 0, 1, 1. The number of states I have is 3 plus 1 equals 4. However, in the case of the mealy machine, it reduces the number of states that I use, such that for an n-bit sequence, I'm only going to use n states. The most important takeaway here is in the mealy machine, I need to know where my outputs correspond to that input sequence, and at the same time, when I'm in that final state, where that input of 0 or 1 allows me to transition to. So just a quick comparison here between mealy and more machines. For a mealy machine, the output depends both on the present state and the present input, whereas in the more machine, it only depends on the present state. That's why we denote the outputs inside of the bubble of the more machine. Whereas in mealy, we denote it from the state that we are transitioning from, as well as in combination with the input. Mealy machines generally have fewer states, as we just saw, whereas the more machine has, as the name implies, more states. The value of the output function in a mealy machine is a function of the transition and the changes when the input logic on the present state is done. The value of the output function is a function of the current state and the changes at the clock edges whenever the state occurs. Right? We're starting to talk about clock edges here, and we'll see how clock signals are going to come into play. Finally, in mealy machines, they react faster to inputs, and they generally react within the same clock cycle, whereas in more machines, more logic is required to decode the outputs, resulting in more circuit delays, and they generally react 1 clock cycle later. All right, so the next thing to look at is the lab script on finite state machines, which is going to allow us to have a look at some VHDL code for writing code for a finite state machine.